good afternoon. I apologize that I'm not here with you today, but there's a few things that I'm going to have you do. So we've been talking the last 2 days about this idea of conservation of energy. So we're going to talk a little bit more about today by doing one more conservation of energy practice sheet. And then at the end of the class, I got a 10-question energy assessment that you're going to do. Shouldn't take you too long, just a little bit to make sure that you've understood what we've talked about so far. Just a couple announcements before we get started. So your e-learning that you did on Tuesday, those 10 questions you did on Schoology, hopefully that is done. If that is not done, you need to get that done this weekend, so that because that grade is already in the grade book. And then if you'd like to do test corrections with me and haven't talked to me yet, please do talk to me when I get back on Monday. We can set up a time during SRT to work on test corrections. Okay. So what I'd like you to do first is I'd like you to, in your notebook, turn to the page of your notebook where we talked about conservation of energy. So this was the last page of notes that we took yesterday, beginning of the period yesterday. So it looks like this. So you're going to have this in front of you because we're going to use this today. But remember, the idea of conservation of energy is that the total energy of a system does not change. It is true that energy can be transferred to different types, but it cannot be created or destroyed, right? And so we talked about this idea of a roller coaster that rolls down a hill. It might start at the top with a lot of potential energy, but as it rolls to the bottom, it loses potential energy, but the potential energy doesn't disappear. It's not destroyed. It turns into kinetic energy, right? And then as it goes back up the hill, some of that kinetic energy becomes potential again. But the key is that if I add up the energy at any point in time, the total energy adds up to the same number each time because the total energy of a system does not change. So there's that. So that's the idea of conservation of energy. Now, there's a few other things that we're going to talk about with conservation of energy today. So I'd like you to get out this worksheet, and if you haven't gotten it yet, I'm going to have the sub pause the video for a second to make sure that you all have this more conservation of energy worksheet with you. And the idea of this is, I just want to think about this in a little bit more conceptual way. Pardon me, what is it? I beg your pardon. What does it mean to say that energy is conserved? So I want to start by talking about, for example, an archer who's shooting a bow and arrow. If you think about holding a bow and arrow and kind of pulling the arrow back, think about what's happening there is you've got some potential energy while you're holding the bow back. If you look in your notes on the previous page, we can look at what kind of potential energy it is. So with the bow, what we've got is that's an example of some elastic potential energy. So what's happening here is when an archer gets ready to shoot a bow, she pulls the arrow back and she gives the arrow some elastic potential energy. All right, then what happens when she lets go? Well, when she lets go, the arrow is going to fire forward, so there's some elastic potential energy, and she's going to release all that elastic potential energy by letting the bow go, and but it doesn't disappear. It has to turn into something, and in this case, it's turning into energy to make that arrow move. What do we call the energy of motion? The energy of motion is called kinetic energy. So in this case, the elastic potential energy turns into kinetic energy. Okay, so that's an example of a transfer of energy. So if you think about this kind of like the lab we did yesterday, remember you had the two bars in the lab. You had 1 bar of potential energy, 1 bar of kinetic energy in the lab on the computer. So what would happen is you would have like a lot of elastic potential energy and no kinetic energy. And as you fire the bow, the potential energy is going to go down and the kinetic energy is going to go up by the same amount, because all the elastic potential energy turns into kinetic. Because again, energy can transfer types, but the total should be the same. All right, what about driving in your car? What kind of energy do you have if you fill up your car with gas? We've talked about this a few times. Right, so if you fill your car up with gas, you're starting here with some gas as a way of storing some chemical potential energy. So it's stored energy because your car's not moving yet, but it's stored in the gas, which is a chemical. So we're going to start with some kinetic potential energy. And the point is that when you drive, your kinetic potential energy, your engine is going to convert that into some kinetic energy. Because now your car is moving. So that's, again, an example of all the chemical energy turning into kinetic energy. And then we've got this last one here. You throw a beanbag up to your friend who catches it from the third-story window. So let's think about it. If you throw a beanbag, the moment that the beanbag leaves your hand, what does it have? Well, it's moving, right? If you throw it, it's moving. So right here, this beanbag is moving up. So if it's moving up, what kind of energy does things have when they're moving? Well, this time it has kinetic energy. Now I want you to try and think about, I'm going to pause for a second and let you just try to think about what you think this kinetic energy is transferring to in this case. So take a few minutes to think about it and write down if you think you know the answer. All right, so hopefully you saw that what's happening is as it's going up, right, it's getting higher and higher. What do things that have height have? Remember, they have a different type of potential energy, but the potential energy you get when you go higher is gravitational potential energy. So here's an example of kinetic energy turning into gravitational potential energy. And then if somebody up here caught it, right, they'd have a lot of stored energy, and they could drop it later and turn it back into kinetic energy. That's just kind of another way of thinking about the same sort of discussion we've been having about conservation of energy. All right? Now, number 2 is a problem like you've done before, right? So I'd like you to take a moment to see what you can do with number 2. So number 2, this is a picture of a pendulum that's swinging back and forth. So what I'd like you to do, it's saying that this pendulum's starting up here at A, and at A it's saying it's got 0 joules of kinetic energy, it's got 2.4 joules of potential energy. And as that pendulum swings, it's asking you to fill in the blanks about what the other energies are. So I'm going to ask the sub to pause this video for about 5 minutes and have you work. So pause the video for 5 minutes. And then resume it after 5 minutes have gone. So hopefully what you found here is that here at the beginning, I know I've got 0 joules of kinetic, 2.4 joules of potential. So what that means is that I've got a total of 2.4 joules of energy. If energy is conserved, what that means is that this total must stay 2.4 joules for every instant in time. So, let's think about this then. If the total has to be 2.4 joules, and in part B, at location B, I've got 2 joules of kinetic, how much is left to be potential? Well, 2.4 minus 2 is 0.4 joules, right? Now at the bottom here it's saying that I have 0 joules of potential. How much is kinetic then? Well, 0 plus 2.4 is 2.4. And then the pendulum swings all the way back up to here. Now up here, you'll notice I'm at the same height that I was over here. And so what we're going to say is that that means we have the same potential energy that I had up here, which is 2.4, which means that the kinetic is 0. All right. Now, number 3 is very similar to this one. So you're going to do the same sort of thing in number 3. I'm going to ask you to ignore these lines that say V for the time being. I'd just like you to try and fill in all the PE and KE blanks for now, and then we'll talk about the velocities in a minute. So I'm going to ask the sub one more time to pause the video for 5 minutes while you try to fill in the PE and KE blanks here. All right, so hopefully you found that the total energy here is 100 plus 0, which is 100. So if there's 50 here, there ought to be 50 there, because 50 plus 50 is 100. Now, this one's got 2 blanks. What are we going to do with this? Well, you should notice that this ball is at the same height. If it's at the same height, it actually means that it has to have the same potential energy, right? And then again, we have to have it add up to 100, so if that's 50, then that's 50. And then on the ground is when you have 0 potential energy. So if you have 0 potential energy, how much kinetic you have? You have 100. All right, let's see what we can do with these calculations then to figure out what the velocities of this ball is. So here's what I'd like you to do. Let's read this statement here and see if we can figure out what our knowns and unknowns are. We're trying to find the velocity at the top, in the middle, and at the bottom of the motion here. So let's read what it says. It says, consider the falling and rolling motion of the ball in the following 2 resistance-free situations. In one situation, the ball falls off the top of the platform to the floor. In the other situation, the ball rolls from the top of the platform along the staircase-like pathway to the floor. Fill in the blanks for the 2-kilogram ball. Interesting. What do you think we got there when it said 2 kilograms? Well, kilograms, we remember, is a mass. So part A, we're trying to find the velocity of the ball whose mass is 2 kilograms at the top. Do we know anything about this ball at the top? Well, you'll notice we know the PE and the KE. If I want to find velocity, which of these is important? Well, let's remember the equations. PE equals mgh. Again, this is right from your notes. Right here, PE equals mgh. And we also have a KE equation. KE equals 1/2 mv squared. Which of these units, which of these variables is going to be helpful for finding velocity? Well, velocity is in this equation, so I'm going to say KE is what I want. And my KE up here is 0. Now let's see if we can solve for velocity. Well, if I use that equation, KE equals 1/2 mv squared, and I plug my numbers in, I would have 0 equals 0.5 times 2 times v squared. So, how do we solve that? Well, let's get our calculator out. If you don't know what 0.5 times 2 is, but maybe you do, 0.5 times 2 should be 1. So we get 0 equals 1v squared. I'm going to divide both sides by 1. 0 divided by 1 is 0, so I have 0 equals v squared, which means, what's the velocity? 0 meters per second. That's the velocity of the top. How does this change in the middle? Well, in the middle, I don't have 0 kinetic energy anymore. Now I have 50 kinetic energy. So I still have a mass of 2. I'm still looking for the velocity, but this time the kinetic energy is 50. And then at the bottom, right, the mass is 2. The velocity is what I'm looking for, and the KE is 100. Oops, I beg your pardon for that. If you would, I'm going to have the sub pause the video again for another 5 minutes for you to try and work out B and C. So 5 minutes, and if the sub could resume this video after 5 minutes of waiting. All right, so this one, KE equals 1/2 mv squared. So if I plug in 50 equals 0.5 times 2 times v squared. So that's 50 equals 1 v squared. Divide both sides by 1. I get 50 equals v squared. And the last step is I have to square root both sides. The square root of 50 is 7 point something, if I'm not mistaken. 7.07 is what I'm getting. So the velocity here is 7.07 meters per second. And look, we just found the velocity here and here. Let's try the last one. 5 times 2 is 1. So I get 100 equals v squared. Square root both sides. I should get 10 meters per second. That's going to be what this one is. All right, sorry, you can't see that. I put my 10 there. All right, I'm going to have the sub pause for a minute while so that you can turn this paper in and then pass this paper out. But I'm going to ask the students to please don't do anything with this yet, because after the video pauses again, I'm going to explain a couple things I need you to do with this. So again, if the sub could collect this paper and pass this paper out, but students do not write anything on this paper yet. All right, so now hopefully you've got this now. So I want to give you a couple things here. I would like you to make sure that you write your name here in this box. That's one thing I'd like you to do. I'd like you to make sure the number that's on your notebook, that goes right here. So I'm going to say that mine was 123, but whatever your number is, that goes here. If you don't know your number, you can just leave it blank, and I'll take care of it later. But it's helpful to me if you know your number, write it there, and then bubble in these bubbles to answer it. All right? And then what you're going to do, you can write on any of this, but the questions for your assessment are right here. You bubble in your answers right there. I will say that there'll be a couple questions that refer to this picture, so you might use this picture to help you for some of the questions. But you bubble in your answers right here, and then when you're finished, you can just turn it face down, and at the end of the period, when everyone's finished, the sub can go ahead and collect this for me. You should not be talking to anyone while you're doing this, but as always, you are allowed to use your notebook, and you are also allowed to use your calculator. All right, I thank you for being on your best behavior for the sub today, and I will see you on Monday. So try your best on this, and then again, like when everyone's finished, the sub will go ahead and collect this. All right, have a good weekend.